Hello, and welcome to the channel, everyone. Today, we will be looking at indices and exponents, also known as power terms. Let's start with an example. Imagine a base number raised to an index, like when we take the number 2 and raise it to 5. Here, the index 5 appears as a small number at the top right of the base 2. The size of the result depends on the index. If we keep the base the same but increase the index, the number gets larger. For example, if we compare several terms with a base of 2, the one with the highest index, which is 5, will have the largest value. Power terms represent repeated multiplication of the base number by itself. The index tells us how many times we multiply it. For example, when we raise to the power of 5, it means we multiply 5 2's together. Similarly, when 2 is raised to the power of 1, it just remains as 2. We refer to this as 2 to the power of 5, or simply 2 power 5. The number 2 is the base, and the small number 5 at the top is the power, index, or exponent now. Let's look at some important rules of indices that help in solving exponential equations. We consider real and positive base numbers and indices in these cases. The first rule is the product law. This tells us that when we multiply terms with the same base, we simply add their indices together to get the new power dot. Next, we have the quotient law. This states that when dividing terms with the same base, we subtract the indices to determine the new power. Let's take some simple examples. For the product law, when multiplying 2 with an index of 2 and 2 with an index of 3, the result is equivalent to multiplying 5 2's together. This can be rewritten as 2 raised to the power of 5. For the quotient law, when dividing 2 with an index of 5 by 2 with an index of 2, we are left with the multiplication of 3 2's. This gives the same result as to raise to the power of 3. The new power is obtained by subtracting 2 from 5. The third rule, the power law, applies when a term that already has a power is raised to another power. In this case, the final power is determined by multiplying the two indices together. If we take 2 raised to the power of 2 and then raise it to the power of 3, it means we are multiplying 3 2-squared terms together. Using the product rule, we can add up all the indices and get 6 as the new power. Alternatively, instead of adding, we can simply multiply the two indices, which also gives 6. The next two laws are related to the distribution property. This means that when an index is applied to a term inside brackets, it can be distributed to each individual part, whether it's multiplication or division. For multiplication, base consists of two numbers multiplied together and raised to a power. The index applies separately to each number. Similarly, for division, when a fraction is raised to a power, the index applies to both the numerator and denominator. Now let's talk about special index values. Any real number raised to the power of 0 always results in 1. To understand why, we can rewrite a base with an index of 0 in terms of subtraction. Using the quotient law, it becomes a fraction where the numerator and denominator are the same, which simplifies to 1. When the index is negative, the result is the reciprocal of the original term. This means that raising a number to a negative power gives 1 over that same number with a positive power. To see why, we can express a negative index using subtraction. Applying the quotient law, we end up with a fraction where the numerator is 1 and the denominator is the base raised to a positive power. The last two laws deal with fractional indices. When a base is raised to a fraction, the denominator of the fraction represents a root. For example, when raised to 1 over a number, it represents that number's root. If the index is a fraction with a numerator greater than 1, the base is first raised to that numerator and then the root is applied. The denominator of the fraction goes outside the root, while the numerator stays as the power inside. That's all for the laws of indices. Unfortunately, these rules will not be provided in the GCEO level exams, so it's important to practice applying them. With enough practice, they become much easier to use. These laws are especially helpful for solving exponential equations, where the unknown is in the power. For example, if a number is raised to an unknown index and equals another value, we need to solve for the index. One useful technique is to express both sides of the equation in terms of a common base. Once the bases match, we can simply compare the indices. For example, if two expressions with the same base are equal, then their indices must also be equal. Let's apply the laws of indices to solve exponential equations. Take some time to try solving these questions yourself, or feel free to skip ahead to see the solutions. For part A, we first rewrite 9 as a base of 3, since 9 is equivalent to 3 squared. Similarly, we express 36 in the denominator as 6 squared. Next, we observe that both terms on the left share the same exponent. We can multiply their bases, resulting in 6. On the right side, the fraction can be rewritten using a negative exponent of 2. With both sides now having a common base, we compare the exponents and determine that z is -1. For part B, we express 1 as 5 raised to the power of 0, since any number raised to 0 equals 1. With a common base of 5 on both sides, we equate the exponents and solve for k, obtaining values of either -5 or 5. Now, let's move on to more practice questions. In part A, we first convert both terms. On the left side, to base 2, next, we separate the unknown exponent, 2x, from the known exponent, -3. Using the product rule, we rewrite the term as a product of two factors. At this point, we recognize that a common factor appears. Factoring and simplifying, we arrive at an equation where one side equals 1. Since any number raised to the power of 0 equals 1, we conclude that x must be 0. For part B, we follow a similar approach by reducing all terms to a simpler base of 2. The first term, 4, is rewritten using base 2. We then separate the known and unknown exponents, isolating the term that contains the unknown exponent. Using substitution, we replace this term with a new variable. This transforms the equation into a quadratic equation, which we then solve. The quadratic equation yields two possible solutions, 1/4 and -2. However, since exponential expressions are always positive and can never be negative, or 0, we reject -2. This leaves us with 1/4, which we equate to the original exponentiated term. Solving for x, we find that x is -2. This next question here is a simultaneous equations question, but it involves exponential equations. Do pause the video and take some time to attempt the question if you would like to challenge yourself. Once again, we reduce all power terms to their simplest base. For the first equation, base 3 is used, while for the second equation, the simplest base is 5. Using the product and quotient laws, we combine the power terms together in each respective equation. For the first equation, we express 1 as 3/2, the power of 0, since anything raised to the power of 0 is always 1. For the second equation, on the right-hand side, we express the fraction using a negative index. The purpose of these transformations is to have the same base on both the left-hand side and right-hand side of the equations. This then allows us to equate the powers and solve for x and y. Comparing the powers in each equation, we get x plus for y equals 0, and 3x minus y minus 7 equals -6y from the first equation. We express x as the subject, which equals negative for y. Using the substitution method, we substitute x into the second equation. This gives us an equation entirely in terms of y, and solving for y, we get -1. Putting this value into the third equation, we solve for x and find it to be 4. Indices and exponents are commonly used in various growth models to study how populations change over time. This can be applied to human population growth or bacterial growth. For instance, the population growth in a village can be modeled by an exponential equation. Here, t represents time, usually in years. So for the initial population, we substitute t as 0, and this gives us 1,000 as the initial population number. We can predict the total population in 10 years' time by substituting t as 10. This gives us 1,349, meaning there is a net growth of 349 in bacterial growth. If a bacterial culture doubles every hour, then the total number of bacteria after n. Hours can be estimated by 2 raised to the power of n. Another application is in the calculation of compound interest, where we calculate the accumulated interest earned from both the principal amount and previously earned interest. The formula accounts for the principal amount, interest rate, and time, usually in years. That's all for now. By practicing more, solving exponential equations using the laws of indices becomes more intuitive. I hope you found this video useful. Feel free to post your comments or questions down below, and let's have an open discussion. Thank you all, and of course, remember to stay curious, keep learning, and I'll see you in the next one.